Welcome to the Deep Dive Books channel, where we hope you find something valuable every day.
Let's continue our interpreting of Max Bennett's A Brief History of Intelligence. This is part 8. There is an interesting phenomenon in biological evolution called exaptation. It refers to a trait that evolved for one purpose, but later found to solve new problems as well. For example, feathers first evolved, in the ancestors of birds, to keep warm, but later turned out to be perfect for flight. We mentioned a similar example earlier. The hippocampus in the brain originally evolved to encode geographic information, helping us form a mental map and know our position. Later, this encoding ability combined with the neocortex, allowing the hippocampus to encode episodic memories, turning our experiences into long-term memories. The wisdom of evolution is truly remarkable. In our previous video, we mentioned that primates developed the theory of mind to navigate political conflicts. Of course, saying to navigate is not entirely accurate, as evolution is driven by random mutations, not by desires. But it is indeed a way to solve problems. Resources are limited, and zero-sum games and conflicts are inevitable. Since we live in groups and desire peace, political maneuvering becomes necessary. However, the theory of mind also has an exaptation effect, bringing us two new abilities. It is these two new abilities that give us hope to escape zero-sum games and pave the way to financial freedom. Of course, this is a very long road. From primates developing the theory of mind to today's humans enjoying freedom and equality, it has taken 10 to 20 million years. But the path is clear. You will see that these two new abilities are incredibly modern. One day in 1990, a group of neurophysiologists was conducting experiments on monkeys. They had inserted electrodes into the monkey's neocortex to study the relationship between the brain and hand movements. The premotor cortex of the neocortex is responsible for simulating and planning mid-level motor goals, while the motor cortex handles smaller motor goals. Certain areas of these cortices correspond precisely to each movement the monkey makes with its hand. For example, when the monkey grabs something, a specific area of the premotor cortex lights up. When it makes another movement, a different area is activated. The research was quite successful, and the experimenters were satisfied. At that point, they made an unexpected discovery. An experimenter picked up a sandwich and was about to eat it when suddenly a noise was heard. It was the sound of a monkey's brain electrode, indicating that a specific area of the monkey's brain had been activated. The researchers looked and found that it was the same area in the premotor cortex that corresponds to grasping something with the hand. This was puzzling, because the monkey hadn't made any movement at that time. The monkey was just watching a person grasp the sandwich, so why was its corresponding brain region also activated? Over the next 20 years, various studies showed that, when primates observe others making movements, such as finger movements, tongue extensions, mouth movements, or even actions spanning several brain regions, certain corresponding areas in their brains also light up, as if they themselves were performing the same movements. I think you can relate to this feeling. For instance, when watching an action movie, you do nothing, yet you feel a strong sense of involvement, as if you are the one performing those actions. Researchers discovered that some neurons in these brain regions are activated not only when one performs an action, but also when watching others perform the same action. They are called mirror neurons. This mechanism is somewhat mysterious. Why does observing someone else trigger an automatic response in oneself? How is this mirroring established? Within the framework of the theory of mind, mirror neurons become easier to understand. They are essentially simulations of others' intentions. When you see someone performing an action, you infer their intention, and then imagine and simulate yourself doing that action, causing the corresponding brain region to become active. This is a very advanced form of simulation. We are not just simulating how the action is performed, but also the intention behind it. For example, when a primate sees someone picking up a box, it not only simulates the action of picking up the box, but also estimates the box's weight and imagines how much force is needed to lift it. When it sees someone reaching for a tool, it imagines what kind of tool to grab. It is this intention-based simulation that makes imitation learning possible. All the reinforcement learning we've discussed before, and the simulation and planning within the mind, are based on one's own exploration. We've never talked about a scenario where a teacher teaches you something. This is a high-level ability unique to primates. From a scientific perspective, it's surprising that primates have the ability to teach. This knowledge has only been confirmed in the past 20 to 30 years. Suppose there is a skill you do not know, and someone voluntarily teaches you. You watch them a few times, imitate them, and gradually learn. This is remarkable. It requires the theory of mind and intention-based simulation. This type of learning has 3 characteristics. The first characteristic is that both teaching and learning are proactive. The teacher genuinely wants to teach, and the student genuinely wants to learn. For example, a mother chimpanzee teaching her child how to crack nuts with a stone. Researchers found that, when a child is watching, the mother will slow down her nut-cracking movements to make sure the child can see clearly. Not only that, but she also observes the child while performing the actions to ensure that they are focused on learning. Doesn't it feel like listening to a fairy tale? Another example is a chimpanzee demonstrating how to fish for termites with a stick. It finds a branch, strips off the leaves, and inserts it into a termite hole. The termites crawl onto the stick, and the chimpanzee can then pull it out and eat them. When teaching this skill to a child, the chimpanzee will bring 2 sticks, using one for itself and giving the other to the child to imitate. This clearly shows the intention of, "I teach you." The second characteristic of primate teaching is that the students genuinely learn. Why does the mother get food, while I do not? You need to understand that this is because the mother has a skill that you do not have. Some chimpanzees take a long time to learn how to use a stone to crack nuts, but they are persistent and continue learning. This is not the same as reptilian reinforcement learning, where you receive no rewards for a long time. The third characteristic is even more impressive. The student can distinguish which actions of the teacher are useful and which are not. In an experiment, a human expert opened a box with a hidden mechanism in front of a chimpanzee to retrieve the food inside, doing this slowly, for the chimpanzee to observe. The expert intentionally made a few irrelevant actions, like performing magic on the box or spinning it twice. What do you think the chimpanzee did? After the expert repeated the process several times, the box was handed to the chimpanzee. The chimpanzee did not perform the unnecessary actions, but went straight for the useful ones to open the box's mechanism. It clearly understood the intention behind each action. Of course, not all cases are like this. Even today, human teaching can sometimes lack clarity in intentions. I recall taking a martial arts class in college where, including the instructor, no one knew how those moves could be applied in a real fight. We were merely performing a routine, like a gymnastics exercise. When education becomes institutionalized, it often falls short. Even less effective than a chimpanzee. The ability to teach is unique to us primates. Other animals can mimic, but only specific actions, not skills. A mouse, for instance, may push a lever for food, after seeing others do it, but this is not learning a skill, since mice inherently know how to push levers. Similarly, fish, as social animals, may swim in a direction following other fish, but that's a reflex, not learning. True skills involve complex actions, require repeated practice over time, and have a critical learning period. A chimpanzee that does not learn to crack nuts with a stone before age 5 will never learn it. The ability to teach gives skills a social attribute. In one experiment, a researcher taught a single chimpanzee the skill of opening a can, then released it back into its group. Within a month, all the chimpanzees had learned to open cans. Our skills are transmissible, which is why primates can use over 20 different tools, and even make their own, while other animals may only occasionally use one. Teaching allows skills to be passed down. If a group has a smart individual who accidentally invents a new skill, the entire group can learn it and pass it down through generations. As more skills accumulate, primate groups become increasingly smart and capable, able to achieve greater things, and accumulate more wealth. In the next lecture, we'll discuss how the efficiency of skill transmission in chimpanzees is still incomparable to that of humans, but the path is the right one. Primate imitation learning offers insights for AI. Training AI to drive cars or control drones, for example, can be expedited by imitating human actions. The key is not just to mimic various actions, but to replicate the intent behind each action. This approach is called inverse reinforcement learning. If you only imitate actions, without understanding their intent, you may perform some actions incorrectly or excessively, and fail to adjust. Humans, when driving cars, do not rely solely on precise movements, but rather on clear intentions, and constantly adjusting errors. Once AI learns to mimic intent, it can adjust errors independently. The second new ability that the theory of mind brings us is the ability to plan for the future. Previously, we talked about how mammals can make plans, but those are plans for the present. Plans for the current self. However, the theory of mind enables us to plan for the future self. If you can imagine the intentions of others, you can also imagine the intentions of your future self. This is actually quite unusual. You might not be hungry right now, but you can imagine that you will be hungry in the future, so you store some food now. You may not feel cold right now, but you can imagine it will be cold tomorrow, so you prepare some warm clothes in advance. This is what it means to plan for the future. Children under 3 years old do not have this ability. They don't understand why they should look for food when they're not hungry. We know that squirrels store food in autumn to prepare for winter. But this storage isn't intentional. It's a reflex. Researchers have found that, when the lab temperature is lowered, squirrels immediately begin to store food, showing that their behavior is a hard-coded reflex. Squirrels don't understand why they're storing food. In contrast, adult primates clearly have a sense of planning. If a chimpanzee needs to crack open nuts in a place where there are no stones, it will bring stones from far away. If they need to use tools somewhere else, they will prepare the tools 14 hours in advance. This ability to plan is closely related to the primate's habit of eating fruit. Eating fruit is not easy. Many fruits have a ripening period of only a 72-hour window, from maturity to falling to the ground. You must reach the tree during this window. Some fruits have fewer competitors, like bananas. Other animals don't peel bananas, so there's less competition. But for fruits like figs, which are easy for all animals to eat, you need to plan ahead to make sure you are there when they ripen. Chimpanzee groups often travel long distances to collect fruit. They know the location and ripening times of all the fruit trees in a large forest area. They plan where to sleep during the journey in advance to ensure they reach the fruit early the next morning. Some biologists believe that this ability to plan for the future is what made our brains grow larger, a theory known as the ecological brain hypothesis. We mentioned earlier that Robin Dunbar suggested our brains grew larger due to social living and politics, which is called the social brain hypothesis. These two theories do not necessarily contradict each other. They may actually complement each other. Because of politics, we developed a theory of mind. With a theory of mind, we could imagine our future selves, allowing us to plan ahead and manage our environment effectively. These two abilities, teaching and planning ahead, have given us an advantage in acquiring resources far beyond other animals. We are indeed on the right path toward modernization. That's all for today's content. In the next part, we'll discuss the birth of language.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.